Okay.
Oh, there you go.
There we go. I'm resonating. Okay. Hello, everyone. I'm Kai. I'm a journalist at Sifted, and we're going to be talking about generative AI and hardware, whether the rapid advances we've seen in generative tech can be replicated in hardware, and what the future holds. Because recent advances in Gen AI mean anyone can rapidly iterate and ship software. But so far, that is where it has remained. So as we move towards an era of generative system design, in which anyone with a creative idea can generate entire systems, not just software engineers, how can Gen AI replicate this impact for hardware applications? To discuss all of that, I'm joined by Mark, Alex, John, and Hailey, and I'm going to get them to introduce themselves now. Mark, why don't we start with you?
Okay, so I'm the CEO of XMOS. XMOS is a fabless semiconductor company, actually based in Bristol. What that means is that we design semiconductors, we design chips, and we sell chips. That's our business model. But the bit in the middle, the manufacturing bit, we outsource. So we're not a foundry, if you like. We have a novel computer architecture that no doubt I'll be talking about more a little bit later, that we spun out of the University of Bristol about 20 years ago. It's called X-Core, and the reason why we're here is it's a generative system-on-chip solution for modern software engineers. I'll go into more detail later. But it's a pretty exciting time for us. We've shipped 40 million of these things, and the reason for being here, the reason why this is so exciting for us is because some of the generative models, some of the generative techniques are helping us to solve one of our biggest business problems, which is introducing a novel architecture into a community of 100,000 users that have never seen us before.
Thanks, Mark. Alex, give us the pitch.
Hi, everyone. I'm the head of corporate affairs at Synthesia. We're one of Europe's largest generative AI companies, and we have built the world's largest AI video platform for enterprise. So you might have seen Veo from Google or Sora from OpenAI. These are video models that generate cinematic clips. No one's making that type of content in Synthesia, where businesses use our platform to make more informative content. So things like employee training videos, product marketing videos, customer support. And we've grown now to the point where 90% of the Fortune 100 are customers. And I should say, because I'm going to talk about it, I think later on, I also have an advisory role at an AI university in Abu Dhabi, and they've done some interesting work around hardware and software, which I'm sure we can talk about.
Thank you, Alex. John.
Hi, I'm John. I lead the engineering team at a company called Luffy AI, which is a deep tech, sort of early stage company based just outside Oxford, so I didn't have as far to come as some of the other panelists. And we work on a new approach to building neural networks that uses a lot less computing power, and that means that we can put AI inside hardware that does all sorts of exciting things. So we can put AI inside drones, inside electric motors, so on and so on. So we can talk about that in a little bit, hopefully.
And we will. Hailey.
Hello, I'm Hailey Eustace. I'm the founder of Commplicated. We do strategic communications for deep tech companies, but I also am an early stage investor. I started investing about 10 years ago to $500 million fund in America. We did everything from SpaceX to leading edge machine learning and lots of different hardware examples. So I'll be talking more about the early stage side of deep tech and hardware.
Cool, thank you very much. And I want to start by talking about where we are now in terms of Gen AI and hardware, because development cycles of hardware are notoriously long. You can't just bash out a piece of hardware in 15 minutes, which you can now do with software. Vibe coding is very much the tech of the time. But Mark, how can hardware bring down shipment times?
So just to calibrate you there, a chip on a relatively old process will take 3 to 4 years of duration and probably 20 or 30 man-years of effort to tape out. So tape out is when you send the chip to the foundry. That tape-out exercise will cost you, at that moment, $3 million, at least. In fact, if you're taping out for a cell phone, maybe $20 million. So you can imagine the level of paranoia, making sure that that's right before you write that check. So there are big barriers in what I would call the traditional hardware development flow. But I would actually like to sort of change the way we regard hardware. If you look at silicon chips, I'm sure we've all seen them. They're black boxes with legs, with metal legs. They do things like compute. They interface to hardware. They do AI. But from the outside, from the system, you can't tell how they're doing it. So when we're talking about hardware, what we're really talking about is what we've become to know as hardware behavior. The inside of that system can achieve that hardware behavior in many different ways. So what XMOS did back in the early days was to try and reinvent, try and reimagine how hardware is designed to enable software engineers to create hardware behavior so that they can take chips off the shelf, download software, and create somewhere that looks like something that looks like hardware. And it's really all about, of course, it's about computational correctness, but we all know that you can create computational correctness using software. We know that because that's how we verify our chips, but it's also about timing. It's about nanosecond level timing performance. Not just being able to meet those deadlines, but being able to meet those deadlines all the time. So if you can conceive of a software running architecture, a processor that can do those two things, then you can do hardware and software. And the interesting thing about that is it's now a target for generative AI design. And that's how we define a generative system on chip, is something that can give you those guarantees, not just getting the answer right, but getting it right on time, every time, and to allow you to customize its behavior from a generative sort of behavioral layer, if you will.
And just to set the scene even further, have the development times for chips for hardware, has that come down over the last 20 to 30 years?
Not really, not really. So, I mean, generative AI does actually have a place in the hardware design, in the sort of traditional hardware design flow, but it still takes 4 to 5 years and it still costs a fortune. And the reason is people will put more and more technology in those devices. So as the process technology becomes more capable, so the ambition of the engineers becomes more. And that hasn't really changed. If anything, the barriers, the commercial barriers to taping out chips have got even higher.
Okay. Alex, I want to talk about the state of play with human interaction and software development. There have been amazing advancements in generative videos, voices, which allow for human software interaction. Synthesia have just released the much lauded Synthesia 3.0.
Yes.
But what's next in terms of human interaction with Gen AI? How can this translate to hardware?
Yes, but before I answer that question, I'm actually quite interested to ask a question back at Mark. So a bit of context: when I first moved to the UK, I came to Cambridge, so I now feel like I'm in enemy territory. But I started my career at a company called ARM, and I was a CPU engineer there actually. And hearing you talk about sort of tape outs and kind of design cycles and how these haven't changed. And I remember that we were talking back then, so this was again 15 years ago, we were talking a lot about IoT, the Internet of Things. Mm-hmm. And there was this big promise that as these small chips got more and more powerful, we'd able to kind of add intelligence to sort of everyday devices. So if you remember, there were all of these companies selling, intelligent fridges and intelligent washing machines. And I think after there were maybe 3 to 4 years of that sort of being kind of the peak cycle, and then it kind of went away. And I think what's interesting for me now is that we've been able to build these processing engines that can sort of run some of these models on edge devices. And I think it's a bit sort of funny that the conversation that we were having 15 years ago is suddenly more relevant now. And so I think the way I see it is there's definitely, in terms of training models and running models, there's a lot of that still going to happen in the cloud. I mean, we build these large models and to do sort of video generation, video and audio generation. Those will definitely run in the cloud for the foreseeable future. However, we started building agents. So essentially, these are, if you can imagine, these AI avatars that you can talk to. And it's our belief that there's going to be a whole new category of business data that's going to be generated by people talking to machines that we didn't used to have before. Because a lot of times in kind of traditional early days of chatbots, a lot of those interactions were pretty slow. And a lot of people found it frustrating, and they never sort of gained traction. And now, if we have this kind of combination of edge devices that can run AI, smaller AI models for things like text-to-speech or things like natural language understanding, paired with large models in the clouds that can do sort of these kind of like, real-time video generation, businesses will be able to have a lot more data about their employees, about their customers, and use it to improve business processes. Just to give you an example of what that means in practice is, imagine sort of if you're a junior salesperson and you want to understand like how to sell a product. Today, you might get some information about that product. You might have a colleague who's more senior than you, and that colleague might give you, 5 to 10 minutes, a bit of like a little training on how to do it. But with an agent, the agent can sort of assume this role-playing exercise where they're your coach, and you can sort of talk to the agent and practice your sales pitch, if you like, before you actually speak to a customer. But that agent can not just practice your sales pitch, that it can give you feedback. And it can give you feedback based on not just what you said, but how you said it as well. And I think a lot of that data of how you practice your sales pitch, what's your tone of voice, what are your sort of facial expressions, a lot of that can actually sort of be captured by sort of on-device models, because there are also things like privacy, but also things like real-time processing as well. So I think it's very interesting that the promise of IoT, I think, is starting to kind of now come into play with generative AI.
The return of the intelligent fridge.
Yeah.
It's upon us. Hailey, what are you seeing in terms of deal flow at the kind of early stages in like hardware, AI, and robotics? What are you seeing a lot of? What are founders really going at as problems right now?
Yeah, I think AI at the edge has lagged in terms of generative AI and things like that, where you have the NVIDIA huge processing power. And I think it's been constrained by the hardware. So now there's a lot of innovation to make models smaller, more effective with less data, less compute power behind them. But also, you have the huge models that, say, Synthesia will build, but then what do you actually need at the edge? And you don't need all of that. Once you ship a model, then you have something set at the edge, and then how do you interact with it, and what do you actually need there? So there's one company that I invested in that does space sensors. The model that you train on Earth and then you send up to space, you don't need all of that processing power on a satellite in space. So I think there's this sort of diversity of models that are going to be working together, and I think we're seeing a lot of innovation there.
Yeah, and I mean, I think the hardware space, you're right, like it's been slower to pick up in terms of the hype cycle, in terms of investor dollars being pumped in. There's software companies have been the main recipients right now, probably because they can iterate much faster. But Dexery raised about 165 million. They're making autonomous robotics for factories. Neurorobotics, which is a German company, I think have raised quite a lot of money and announced expansion to China today. So there is definitely movement. But maybe we can quickly talk about the limitations in Gen AI at the moment. John, I'm going to come to you first for this. What are the challenges implementing AI and hardware, particularly at the edge?
So there's a number of challenges. I think maybe one thing to sort of illustrate how far we are away from running kind of what people think of as AI in hardware. So ChatGPT, there was a research report a year or two ago that looked at the average power needed to do a query on ChatGPT, and I think it came out with 3 watt-hours. Sam Altman then came out with a riposte saying, no, it's nowhere near as energy intensive as that. An average query is only 0.3 watt-hours. So it depends what the query's doing and whether it's just text and whether there's images and so on. But those don't sound like very big numbers, but just to give a sense, if you've got the latest iPhone in your pocket, it probably has about 14 watt-hours of energy capacity in it. So if the first study was right, by the 5th query, your battery has died. Maybe you can do 50 if you're lucky, if Sam was right and you're just being polite and saying thank you. But it isn't going to last terribly long. So that's one challenge, is just, at the edge, often you're not connected to a power source. Even if you are, you're going to, the other thing, by the way, probably before your battery runs out, you'll have burnt a hole in your pocket. Because that power is literally generating heat, which is where a lot of the energy requirement comes from, as fans to cool. So there's a lot of practical challenges getting big AI models into edge hardware. So that's one. Another one is often that edge hardware isn't actually connected to the internet. So we work a lot with industrial customers who typically don't like connecting their factories to the internet for all sorts of obvious reasons. And then another one is actually kind of just the amount of time that you need to make a decision in often at the edge. So I mentioned we work with drones. So if you're flying a drone and something fails, a rotor fails in the drone, without all else being equal, that thing will drop out of the sky. If you're going to wait for an internet connection out to ChatGPT to ask it what to do next, or whatever, to an AI, by the time the answer comes back, it's no longer flying. So you have to make decisions much, much quicker. We're looking at working on electric motors. You need to work in hundreds to tens of thousands of decisions per second to make a big difference to the energy consumption of a motor. So again, you have to be super small and super fast if you're going to work at the edge. So there you go. There's some challenges.
So trousers on fire and drones falling out.
Trousers on fire, you're out of the sky, and you ran out of time a few microseconds ago.
These are challenges.
Yeah.
Mark, what are you seeing challenge-wise?
I think it's the same. I think for the systems that we sell our chips into, it's generally deeply embedded systems. The primary care about is always how much does the chip cost. That tends to set limits on whether you can have very much memory involved in the system. The secondary consideration is power. And of course, there's a hygiene factor, which is, can you deliver the thing that I'm asking the chip to do? So those are challenging, and where you can't have a reliable connection back to the cloud to augment the experience, then what we typically face is taking models that have been developed in a much more resource rich environment and trying to compress them into an embedded chip. And that will typically mean we have this rather imaginatively named concept of a small language model, which is an LLM that has been tailored down perhaps to a specific use case. You can have a meaningful conversation with your light switch, but it won't answer questions about weather. Those kinds of things you can do at a functional level. And there are many other things like dealing with sparsity and other things that you can do at a more sort of technical level to try and cram these things in, which might start off as being a 10 megabyte model into a 1 megabyte embedded footprint. Otherwise, you can't afford the feature. So those are real challenges. There's a lot of work going on in that area, which makes it quite difficult to pin down exactly what precise hardware support you're going to need. Which again, it feeds into this argument for flexibility, for accessible flexibility.
Alex, let's go back to one of the challenges that John first flagged, generative AI being like really energy hungry.
Yeah.
How do you go about mitigating that? Like, is that a major barrier for AI and hardware? Like, can that be solved?
I think the conventional wisdom so far has been that you just make these models bigger and you'll get the performance gains from that. But especially in maybe with the latest releases, we've seen that kind of conventional wisdom starting to go away. If you think of GPT-5 versus GPT 4.5, that was not a scaled model. So when we went to 3 to 4, it was definitely a scaling up in terms of the model, but 4 to 5 was not as big. It was relatively small. And I think the reason for that is more and more of these models are used to do a reasoning, which requires a lot of hardware at inference. So you need to scale inference time compute. And as a result, that's why you see, I think, a lot of this rush to build data centers is not actually powered by training, it's powered more by inference, because there's a huge demand for reasoning models when it comes to inference. And but what I'm actually optimistic about is that we're making progress in not just making these models bigger, not just making the models more capable, but making them smaller as well. So just to give you an example, the university that I mentioned, we open sourced a reasoning model that's very good at math that is similar in performance to GPT-5. It's almost as good in terms of the kind of benchmarks, but it's 30 times smaller. And that means that not only is its kind of energy footprint is smaller, but we've also made it run on this new hardware from Cerebras. And they've built this kind of massive chiplet, essentially, where you can run inference very, very fast. I think it's about 10 times faster than kind of the latest NVIDIA hardware. So we're making progress is the short answer. And I think there's a business incentive to make progress because no one wants a huge electricity bill. But what's interesting is, and doesn't get a lot of attention, is a lot of the data centers, they're either in places with lots of water or lots of electricity or energy. It's very hard to find an intersection of both. So you then have to either find sources of water or to find sources of electricity. And I think this kind of scarcity will make businesses sort of, and AI companies push for more energy efficiency and water efficiency.
John, how can we get these sophisticated models into edge use cases? How can that be done?
So I think it needs, I mean, it's great, the progress that's being made on the algorithms, is clearly important. Moore's law is going to help, but maybe not fast enough. And Moore's law, as in his law was that compute power doubles every N years, couple of years. It seems to be at about 2.5 now, and it's kind of slowing down. So it'll help, but I think if we're going to get there to the point where things can run realistically on the edge and hopefully save a lot of power as well, we've got to look at different algorithmic approaches as well. So the kind of the neural nets that are at the heart of the kind of AI revolution are still, at the moment, they're sort of very big, that are trained on huge amounts of data. And I think the kind of techniques that we are looking, so luckily Luffy is coming to the rescue, right? So we're looking at a very different approach to how you build neural networks, and the approach we're taking, rather than starting with a huge one throwing a lot of data and training, we start with very small ones and evolve them till they just solve the problem they've been set. And so, that means the software requirement is a lot smaller, which means that, Mark's hardware is more likely to be able to run it in a realistic time at the edge. So,
there's been one name that's synonymous with every big headline AI infrastructure story over the past few months, and that's NVIDIA. Everyone is building with NVIDIA. But how do we diversify the hardware that's underpinning all of this, Mark?
So I think it's important to categorize where NVIDIA is present and where it's not. It's present in the data center, and actually most of the sort of glamorous AI models are being run in the data center. So I think NVIDIA has become synonymous with that and synonymous with the AI movement in general. In our world, where XMOS sells its chips in deeply embedded systems, NVIDIA is almost never there. Now, it does happen, and typically It'll be in a situation where you might be dealing with large data sets, for example, high definition video. And then NVIDIA will be only a part of the solution. And normally, the reason why they're only a part of the solution is because you turn on an NVIDIA chip and your battery's dead. So there's a chain of power management intelligence that tries to determine whether or not there is a trigger to switch on the NVIDIA chip. And that's all, generally speaking, not NVIDIA hardware. So I think they've done a very good job of positioning themselves right in the center of this, and in the data center, that's broadly speaking correct. But in the embedded space, they're not nearly as present. There's a lot more diversity, which is effectively evolved as a result of the diversity of the applications that are in that space.
In the embedded space, this is a really high-level question, but like in the embedded space, like what are the key, what's the low-hanging fruit, do you think, to kind of deploy this AI hardware?
That's a really good question. I'm not sure I have a perfect answer to it. I think, generally speaking, embedded engineers are not machine learning people, so it's a different skill set. Vendors like us, we need to bring building blocks that are based on machine learning alongside the building blocks that we bring that are based on signal processing or control processing and so on. So we need to basically pre-package them, unit test them, make sure that they time correctly, and then allow our customers to use them as a sort of a black box. And at the same time, partnering prolifically with companies that are building data models. So that's the way we run our business. And I think that's the way that scales. You know, we're, relatively speaking, a smaller player in this space, but if you look at the vast companies with billions of dollars of revenue, they're doing the same thing. And the reason is the massive diversity of AI models. You know, we may talk about voice models, local dictionaries. If you go to a place like India, there are many different languages and many different dialects. So even a single voice model for controlling a ceiling fan in India actually breaks down into probably 50 models. So that level of diversity is just unmanageable as a semiconductor company. It requires specialists. So partnering with those specialists is really important.
Okay, let's stick on this kind of slightly future-looking, near to medium-term trend. Hailey, I want to come to you. Hardware's cost and long time frames, like investors often cite them as reasons not to invest in hardware. And that's typically the reason why most VC dollars has gone towards software. Could generative systems design change that?
100%, yeah. I mean, you take something that takes 4 to 5 years and millions of dollars. By the time you think of what you want to do, and then you put it into practice, say you do it that day, it's delivered 5 years later and the market is completely different and irrelevant. So why would you invest today in something that there's incredibly small chances of actually succeeding? But now with generative AI encoding tools, and especially XMOS, being able to code it and ship it in minutes or days, and then once it's embedded, you can actually just go back and change it. Like even if I build a robot and it ships, you know, say next week on XMOS's chip, then, you know, a year later, if I wanted to, I can just go back and update that hardware again with software. So that's a huge de-risking factor for investors, which is amazing. But I also wanted to talk about the diversity element as well, because I think, you know, we think about generative AI, and that's the only type of AI that's out there. But actually, there's so many different kinds of AI approaches, and it's almost like coding languages. So no one just codes in Java or something like that. You use a lot of different types of coding languages. And I think we'll see the same thing for AI in the future. So you might run a model on GPUs, but then ship it to XMOS, or, you know, use neural networks, but then use a bit of neuroplastic AI. I think we'll see a lot of different supply chains almost, like different chains of, like, you have an employee who walks into, say, a McDonald's. We were talking about this in our prep call. They say hello to their Synthesia model, and then it's pre-programmed to talk back to you with, you know, a smaller model that knows it's going to talk to you about a certain thing. And it's this like seamless flow together of a lot of different pieces of hardware and software working together.
Mark, how is generative AI changing how software is coded? Like how and how applications are committed to silicon? Like, what does this mean for the chip industry?
I think it's transformative, and I think one of the things that I've been, as throughout my career, incredibly envious of is how quickly software companies can get market feedback. It takes 3 years to get customer feedback for a startup, because when you engage with a new customer with a new company, their answer is always come back when you've got it. So 3 years later, you come back where you've got something you've sweated blood over, and it may or may not hit the mark. And I think as the IoT is diversifying and actually accelerating, that problem's just getting worse and worse. I often say it's like trying to shoot a swarm of flies with a hunting rifle. You're not going to hit any of them. So actually having the sort of, acknowledging that velocity, I think hardware companies are going to have to change the way they think about these things. They're going to have to empower software engineers with the ability to create hardware behavior, and that's what XMOS has been doing for 20 years. And they're going to have to empower them using high-level tools where they can just describe the behavior of their system. I think for many years, semiconductor companies have been enforcing knowledge of their architecture and programming models on their customer base. And generative AI, with the appropriate underlying hardware, can turn that around, and they can essentially, semiconductor companies can respond to the language of the application. And that is incredibly transformative. So I think the combination of that and the velocity of being able to map generative systems down onto silicon and knowing that you can run it in production at scale in literally minutes or days, I can't overstate how important that is.
The title of this panel is Keeping Up with Gen AI. Alex, is this fair? Like, are hardware and software makers just trying to keep up with this tech?
Yeah, I think it's with the sort of recent advances in reasoning models. I think the hardware requirements have definitely increased. But what I'm optimistic about is that we talk a lot. You even mentioned yourself about vibe coding. So this idea that you can, people who have either no experience or limited experience in coding can just talk to these models, and then the models will generate the code, the kind of C or C type sort of code that would run. What's interesting is that not only is generative AI helpful there, but it's also helpful in then translating that high-level sort of programming language into machine code. So there's this process called transpilation where you now have generative AI systems that can take a high-level programming language and adapt it to any underlying hardware. So you're no longer sort of dependent on a particular CPU or GPU or sort of NPU architecture. You can actually have generative AI from the moment you kind of talk to it to write you some code to the moment where that code actually runs on the machine, sort of generated with AI. And that ability to sort of not be hardware dependent will enable, I think, all of these companies that have perhaps up until now have been limited to kind of see adoption with software. So yeah, that's really encouraging to see.
I'm going to take slight issue with you on just on one aspect of that, which is I agree with you in generally speaking where the code is soft real time, but there are many processor architectures around. I can only think of one very close to home that guarantees real time behavior. So I think you're right in terms of computational correctness. You can choose many different architectures, but if you want that done, if you want that to deliver results exactly on time, under any circumstances, that field of options reduces very, very significantly.
We love slight issues on a panel. John.
So it's just a slight one.
John, I'm going to come to you. What metrics should we be using to measure hardware's ability to keep up?
I heard you, but maybe the others didn't. So yeah, that's a great question. I think I started with one, the kind of power consumption. So I think that's going to be really important to sort of looking at, particularly for situations where you're trying to run at the edge not connected to a power source, but clearly that has a broader benefit in terms of data center costs and so on. So I think some measure of intelligence or inference per watt hour is going to be a hugely important thing to track. I think for us, sort of other metrics that we look at, concentrating on the edge where we have to run inside the hardware that is already there, because our customers typically can't wait the 3 years for a custom chip to be produced. So we're trying to run usually on some kind of ARM-based system inside some piece of industrial equipment, often an electric motor, for example. We'll look at particularly the memory footprint. So how much space does the neural network and the execution take? And then we'll look at the inference time. So for example, memory footprint, we're trying to target typically into tens of kilobytes to fit inside, like in the scenario where we're running inside an electric motor, the power electronics that are inside there and the ARM processors that are inside a typical electric motor, not very powerful these days, right? So if you're not in tens of kilobytes, you're going to struggle to run inside one of those things. So we're working with one of the main manufacturers that makes the sort of control systems for electric motors, and the chip inside their main model is the same chip that was inside a Nintendo DS, if that rings any bells for people. So not very powerful, right? So you got to get the footprint an awful lot smaller. And then the inference time, I kind of touched on it earlier, how long does it take to make a decision? Actually, Alex, you were talking about the kind of, the move to agent-based AI sort of driving that. The networks can't get bigger because they've got to make a decision quicker because you ain't got time to wait. Again, if you're inside hardware, you typically have milliseconds, maybe even microseconds to make your decision. So how quickly can a network make a decision is a huge factor. So.
Okay, let's look further into the future. What does AI, or what will AI-driven hardware look like in like the years and years to come, Mark? Like, what are we going to be playing with?
I think, as I mentioned earlier, in terms of how people are going to engage with hardware, they'll engage with it in the language of their application. They'll engage with it using exactly what they want, describing what they want, as opposed to trying to understand an underlying architecture. So I think that's going to happen. It's mandated by the fragmentation of systems and the fact that so many systems now exist with different demands. That the mapping that onto architectures is becoming increasingly difficult. So it's on the semiconductor companies to deliver platforms that can understand application-level descriptions, behaviors, the like of which we describe when we're doing vibe programming, but with the ability to deliver that with absolute accuracy and determinism on the platform that you're going to ship millions of units of. So I think that's one thing. That's the development flow, if you like. And I think where companies like Synthesia can really add value is that landscape, that future world has 100,000 developers using these platforms, maybe more, right? Because we're not just enabling software engineers, we're enabling product managers, just creative artists to develop systems. And they're going to need coaching, they're going to need help, they're going to need these AI avatars helping them through that process. So I see that being a very key part of it as well. So yeah, I think it's, when you think about it as well, just wandering slightly out of my domain, progress that's been made in 3D printing as well, if you put that together with chip-based design and so on, it's mind-boggling. I think it's going to be very exciting.
Yeah, with all those intelligent fridges, it will certainly be exciting. Alex, for human interaction, how's AI-driven hardware going to shift things in the years to come?
So I'll just take as an example, the device that I'm wearing on my face, which are these glasses that are made by Meta. And today, they're useful in some scenarios. A lot of the scenarios that they're useful in are sort of like casual interactions where I'm asking it to play a song, or I am asking it like the weather. But fundamentally, they're not more powerful than sort of the Google Assistant inside your home device, for example. But if we're going to make these systems more powerful by an order of magnitude while keeping the energy consumptions lower, they'll be able to actually do things for you that are more useful. And just a simple fact that in order for you to talk to these devices, they usually listen for like a wake word, and having that, and that drains the battery very quickly. And having that, implemented a lot more efficiently could be like a massive help, because what happens is after about 4 hours, I have to take these off and charge them again. So I actually have 2 pairs. So I kind of just keep swapping them on and off. And so just small advances like that can make a huge difference, because that means I can just wear it on my face for the entire day, and I don't have to take them off at every 3 to 4 hours. And so I think those types of not just performance but energy efficiency gains will help. And I think on the kind of in terms of like large models, I have this kind of theory that when people talk about superintelligence, it's often very unscientific. A lot of it is like hype. And the best way that I've tried to sort of internalize for myself what superintelligence can mean is basically this world model that's about 100 trillion parameters, but has a few kilowatts of energy. And the reason why I say that is because a lot of times we just think in terms of parameter count, because we kind of try to make a parallel with the human brain, but we forget that the human brain is incredibly energy efficient. And I think we need to push more into that direction as well, not just making these models bigger, but making them like really energy efficient. And I mean here like orders of magnitude more energy efficient.
What are you actually, like, what are you practically using the glasses for right now? Like, do you use the cameras in them often when you're having conversations with people? Is it in a business context, in a personal context?
Right now, you probably haven't got an internet connection, so you're probably not using them at all.
It's mostly for like personal stuff. So I will listen to music. I'll take phone calls on them. Like I said, a lot of the interactions I use, for example, at home, I used to have with these Google or Alexa devices. I just now ask the glasses for like the weather or my calendar, my schedule for the day. So they're beginning to be more helpful, but they're not to the point where, like, my ideal scenario is to have a world model that can run on these devices. Like for privacy reasons and a bunch of other reasons, if I can get something to the scale of a world model that can fit inside these devices, I think you can unlock so many sort of benefits from that. Not just in personal, but for business use cases too.
John, in embodied AI and robotics, what's the future going to look like?
The future's bright. So I think sort of hardware, it's easy to think about hardware as just being the kind of the chip or the compute, but actually I think there's some huge possibilities with putting smaller neural nets inside hardware that will change the way the hardware itself maybe is thought about. So one of the things in the neural net approach that we're using at Luffy is something called neuroplasticity. You referenced the human brain, so the human brain is neuroplastic. We don't come with a pre-programmed ChatGPT model and then just sort of interact with the world without changing. And that's a sort of hugely important aspect when you're thinking about hardware, because it becomes incredibly expensive to try and program something precisely for each set of hardware you're ever going to experience. And even, even once the hardware is out there, stuff changes. So the drone, when it's flying around, the little sensors inside it will wear down over time. The rotor might start performing not the same and so on. And so the neuroplasticity aspect is what will allow the neural nets, the AI, to adapt to the way the hardware is actually behaving, because it needs to learn in the real world that we all live in. We have to learn as we go along. We can't simply be pre-programmed for the world that we're expecting to experience. So where that sort of goes, I think, with hardware is, it will go beyond kind of what we're doing now, which is controlling the hardware that already exists, and then into enabling better hardware to be made. So just to give one example, up the road here is the BMW factory where the Mini is made. So great British car made by a great German company. in a great British city just up the road. It's a very automated factory, huge numbers of robots. So they do a tour, by the way. If anyone wants to experience a high-tech production environment, I recommend the tour at the BMW plant. But those minis are being built by huge robots. And one of the reasons they're so huge is that one of the very hard problems in controlling hardware is precise positioning. They have to arrive at exactly the right point so that your wing mirror gets attached to the right bit of the car or whatever it's doing. And at the moment, those robots are so huge because they have to be very heavy to make it easier to stop them at the right point. But if you've got an adaptive brain inside the robot, you could build a much smaller robot to do the same thing. So that's just one example. So the world can become much more efficient. So I guess I want to sort of leave with a message of hope, I guess, that there's lots of AI things that will help us spend less energy and use less of the world's resources, as well as the kind of headline stuff right now, the other direction.
You heard it here first. The neuroplasticity, I think, is a really interesting point within models and within hardware. That's really been the promise of something like autonomous driving for about 30 or 40 years now. And it still hasn't been achieved. There's tens, if not hundreds of billions being pumped into these sectors. Yeah. What's taken it so long? Why is this so difficult?
So I think, a short answer would be backpropagation. So the algorithm inside inside most AI approaches right now is deep neural networks, and the way those networks are trained is by throwing data at them and then using an algorithm called backpropagation to tune the weights inside those networks. So sorry, I'm going a bit nerdy, but that algorithm can't work with neuroplasticity inside it. It needs, once the weights are trained, they have to stay as they are until the next iteration of training and so on. So a different approach is needed in order to build a network that looks like the human brain does, where actually, so what we do is we adjust our weights as we go. So my example of this is not a human example, it's an animal example. If you see a baby horse being born, a baby horse, a foal, will very quickly learn to walk, right? It doesn't walk straight away, and you'll see it sort of staggering around and sort of slowly getting used to it, and within a few minutes it is now walking. That's neuroplasticity in action. So it's got a pre-built neural network in there, but the weights can change. And the weights change because it's learning, okay, this is how long my legs are, I'm on rough ground, it'll slowly adapt itself. So that doesn't work. You can't do that with the algorithms we've got for training networks right now.
Hailey, what does the future look like for deep tech investors like yourself? Where do you see yourself spending a lot of time looking at deals in the years to come?
Yeah, I think there's a lot of innovation on the software side, on the algorithmic side, like Luffy. And I think also on the non-consumer side, potentially, I think the consumer side is kind of dominated right now by the OpenAIs of the world. But I think in the more like quote unquote boring areas, Ewan Blair in his talk earlier was talking about how, we haven't really seen this GDP level change in AI adoption yet. Like, I think he said that Accenture earned more in revenues consulting about AI than OpenAI actually earned delivering AI. And I think hardware and the edge is actually where we're going to see that GDP level change. And there's this interaction between the innovation on the algorithm AI and model side with neuroplasticity, with lighter weight models, but then that will also affect hardware and on accessing more flexible platforms like GenSocs. I think that will also open it up to a much wider group of people because you don't have to have a hardware engineer in your team to be able to make something. You can just, start coding, ship something, and it's ready to go. You don't have such a heavy lift on the hardware side, so I think we're going to see a lot more in the next 2 to 3 years, a lot more interesting innovation, implementation, actual use cases at the edge where you can, save 10 million in energy costs in a factory, or, be able to buy smaller robots because your AI control system is better. So I think like seeing those actual real world benefits rather than just, look, I can talk to an AI girlfriend or whatever. Like, I think that's where we're going to see real exciting business use cases.
I want to ask one more question, but then I'm going to come to the audience for a Q&A session. But Mark, I want to just finish on, like, in 10 years' time, are we still going to distinguish between software and hardware design? Will generative systems, will that have just blurred that boundary?
I think it already is. But yes, I don't see any going back. I think it's just going to become more and more unclear and unimportant, actually, how behavior is delivered, whether it's delivered by executing code on a machine or by hardware gates. I think there will be a tendency towards using code because of the factors that we discussed previously. There are so few bets that you can place nowadays where you're willing to put $20 million down and wait 3 years. That I think is going to become something we look back on and say, wow, whoever did that, right? In the next 10 years, I think we'll look back and think that was a ridiculous way to run a business. So I think it's going to become more and more important that we can soften a lot of the hardware stuff that we do today, but that doesn't mean soften its behavior. It has to behave like hardware. If things don't arrive on a hardware interface, they're late. Things break.
Yeah.
Robot arms hit cars.
Yeah.
Drones fall out of the sky. The missing deadlines in hardware is not an option. So anything that we do in software by coding has to respect those parameters, as well as getting everything computationally correct. So I think we're, GenSoc is absolutely a very strong step in the direction towards defining systems at a behavioral level, where as long as that system delivers functional correctness, a tolerable amount of power consumption, it costs the right amount, and it times, so it's on time every time, there's no reason to start regressing back to hardware solutions.
Does anyone have any questions for the panel at all? We've got a couple. That's good to see. Okay, we'll come to the gentleman in the blue top. Have we got a roving microphone? We do indeed.
Hi, can you hear me? There we go. I was wondering if you could share some opinions on the batch invariance problem as reported by Thinking Machines Lab.
Sorry, we're just playing around with the volume levels. If you can give us the question again, that would be great.
Yeah, how's that? I was wondering if you could share some opinions on the batch invariance problem as reported by the Thinking Machines Lab. Familiar with it? And how you might recommend monitoring for that, or how you've seen it solved for on the data center side?
This is the batch invariance problem.
Mm-hmm. Not sure what it is.
We can't take that.
Okay,
that one's gone way over our heads, I'm
underload when the
afraid.
math goes sideways and the inference gets poor.
Sorry, can we get a little bit more volume on the microphone? We can't get any more volume on the microphone. Okay, would you mind coming forward? We can, there's a couple of seats here. We can just take your question.
Speaking to this. There we go. It was a question about the batch invariance problem reported by the Thinking Machines Lab, where under heavy load, inference goes sideways, the math gets poorer, and suddenly inference quality really goes down. Is there anything that you could suggest, methods to monitor for that, so that on the application engineering side you can see it coming, or ways that you monitor that on the hardware side?
I say so that sort of challenge is something that I mean, to be frank, that's a specialist question that we would normally partner to try and solve. So I don't know if John's got any comment on that. Sorry, I don't want to throw you a hospital pass here.
That is okay.
But just to sort of clarify, XMOS is a semiconductor company that deals in functional pre-verified blocks that our customers stitch together. And GenSoc is allowing behavioral descriptions of how that's done. So the question you asked, I can't provide you with a great answer to this, unfortunately, but the question that you asked would be something that we would be asking of our partners when they're delivering models to us, and to some extent on specialists in particular use cases.
Okay.
Sorry.
Thanks, Mark. We're going to go just here. I'm going to use my microphone because I think it's a bit louder.
Thank you so much. Should we buy or rent the hardware for AI since the depreciation is getting faster and faster?
Great
Thank you
question.
very much.
Great question.
John, why don't you kick us off?
It's going to cost you a lot of money either way. I don't know. We buy ours, but that doesn't mean I necessarily recommend that to you. But yeah, we run our own compute with our own GPUs and training process.
Mark, buy or rent?
This has been a decades-old conversation in business models in embedded systems, because everybody wants to monetize software in the same way, monetize hardware in the same way you monetize software. I don't think anyone's managed to do it. And certainly in the embedded space, unfortunately, you buy, you consume, and you buy again and again and again, which I think is why it's important to be able to do in-field upgrades to try and preserve the time in market. Yeah, I think in the embedded space, we probably will continue to buy. It's unfortunately been a challenge to change that.
Hardware as a subscription. Still a little bit far off then. Okay. We've probably got time for one or two more. We'll come over there. Perfect.
Haven't heard much about the mathematics. To what extent are you actually monitoring developments there? Because I heard backprop mentioned, so chain rule, differentiation. I could mention Cauchy, methods of steepest descent. That's where the real power lies. That's where the real sort of development lies, in my opinion, as opposed to more compute. Discuss.
I agree. I think, I mean, it is all, neural nets are all maths, right, really. And I think right now, the sort of, I mean, the G in GPU is graphical, right? I mean, we got lucky that those things were good at doing matrix multiplication. That doesn't mean they were optimized for it. And I know there's a lot of people looking at optimizing chips for the training aspect. For me, I think where it gets interesting is at the execution end. So when we're thinking about kind of running at the edge, so where I would love to be at some point is some kind of neuromorphic type hardware that actually it exists to just run inferences on networks, which is will collapse to doing matrix mathematics. But it's sort of, I think increasingly the hardware will be less about running a kind of a classic sort of central processing unit program executing steps of instructions, and instead we'll be doing an awful lot of math. And I think you can build chips that are more optimized for that, for sure.
Okay, thanks, John. I think we've got one more question over there.
Hello. Yeah, primarily another one for John, but just working in this industrial IoT sector where you've got it's decades-old SCADA and PLC systems, and how, I mean, it just seems like a disconnect, and you've got some generative AI at the front end. How does that, presumably you've overcome this, was that difficult to overcome the connectivity problem? And also, do you see those SCADA systems going away anytime soon?
So, all right, for those who are not familiar with SCADA and PLC as acronyms, so these are acronyms for the kinds of systems that big industry use for kind of automating the stuff that they do. So that BMW plant up the way has, I don't know how many PLCs, programmable logic controllers. They do kind of like, if this, then that type logic to run that factory. I mean, those kind of factories are invested in, those big industrial installations are invested in for 20, 25 years plus, right? The maths of the economics doesn't work if you expect your hardware to completely change in a factory, less than that. So I don't think we're suddenly going to see no SCADA and no PLCs and so on. I think it's going to take time. I think over time they will evolve to using much more kind of neural net type approaches. We are right at the beginning of that journey. You sort of hinted at, and are they ready for it yet? I mean, a lot of industrial customers are very cautious. So that is certainly one of the challenges that we have, turning up saying, hey, we're going to put a little brain inside your thing-making stuff. We're approaching it piecewise. So I'll throw another acronym at you. PID, have you heard of PID? So proportional integral derivative is basically the algorithm that is inside most of those PLCs, most of that industrial control stuff is basically doing maths again, simple maths. I'm going to adjust what I'm doing based on the proportion of what's happening, the integral and the derivative of what's happening, basically. We're swapping that out with little AI controllers. All of the safety stuff that's around it that stops that doing stupid stuff all exists already. So the trick is to swap out the old bit that doesn't do such an efficient job with a new bit that does better, but with all the safety controls around it to stop it doing crazy stuff.
Mark?
So, and that reasures people.
Last word with you.
Yeah, I guess I was just going to pop up and and just comment on the fact that obviously there's lots of installed infrastructure in factories, and much of it is sort of predates some of these technologies. But they are still deploying AI and generative models, aftermarket predictive maintenance solutions, for example. So there's still a place, even in those to sort of, I guess, reinvigorate an old installation. There's still a place for this kind of technology, and it is being used. I can testify to that.
Yeah, and there's a huge appetite for all the big names, the Siemens and ABBs and so on of the world have all got teams working on AI. They're still kind of working out where to put it all.
No one wants to build a factory that they know will be inefficient in 10 years.
Oh,
they
yeah.
don't want to spend
Totally.
200 million and know it's going to be not as good in 10 years.
So the
being
bosses of
able
all
to
those factories
adapt,
are, totally.
That's a good note to leave it on. The bosses of all those factories have appetite. All right, thanks very much. Thank you, guys.
Thank you.